Welcome to the next video in the series on condensed matter theory. In this video I want to talk about the electronic band structure of the alkali metals. And the alkali metals are, if you look at the periodic table, those that you find on the left side, going from lithium, sodium, potassium, rubidium, cesium and francium. So we have a look at the band structure of these materials. These materials have basically one electron per unit cell that adds to the bands of the valence and conduction bands, and the others are deeper in the core because that's a filled principal quantum shell. Now, for graphene, we were able to compare the free electron band structures to an experiment, and we saw that that worked really well. We also saw that with the use of density functional theory, we were able to predict basically the electronic structure of graphene. For the alkali metals, there are no modern band structures available. And old measurements out of the 60s and 70s only measure a few K points. So what we can do is, of course, still do these calculations and see that they are in agreement with the older data. But what I will show you here in this video is basically comparing a full calculation coming from density functional theory with a calculation where we say we have free electrons moving with a parabolic dispersion, as if there is no lattice, such that we can see what the effects of a weak periodic potential in these materials are. So we have the free electron-like dispersion, which is parabolic, and then we get folding at the brilliant zones. Now, these alkali metals are not simple cubic. They are cubic, but they have an additional atom inside the center of the cube, making body-centered cubic, and that changes the brilliant zones. So the brilliant zone looks like a beautiful object in 3 dimensions, as we see here. And again, we can define different points in K-space, the zone boundary in the X, Y, and Z direction, which is a corner of the brilliant zone, we call H. When we walk in the 1, 1, 1 direction, we call the zone boundary P. But you already see that this shape, although it is space-filling when you do the translations, is not a simple structure. And if we do the translation, then you see that you go from gamma to P, so from the center of the zone to a corner of the zone. But then the next brilliant zone, you walk on the boundary from P to H, and then you continue from there back to P, back to gamma. So if you look at the energy momentum dispersion in lithium, on a straight line in the 1, 1, 1 direction, you go from gamma to P to H to P to gamma, so it's a strange path in the brilliant zone. And then we see that we have the bands, and you have a parabolic-like dispersing band going from gamma to P, and when you hit the zone boundary, you get folding and it comes back. When you go from P to H, you see that there are other bands that don't start completely at zero, and that is because they are folded back after moving in a different direction. And well, this can become arbitrary complex for arbitrary low symmetry crystal structures. But you see that lithium is reasonably free electron-like, where the effective mass of lithium is slightly larger than the free electron mass that you show here in thick blue. The Fermi energy sits at 0, so you're basically well below the folding of the additional bands that happen when you look at the electronic band structure in this system. Now we can go one down in the periodic table to sodium, and you see that sodium is reasonably well free electron-like with an effective mass of 1. You also see that when you go from lithium to sodium, that the brilliant zone shrinks. The atoms become larger when you go deeper and deeper in the periodic table, so the real space crystal structure becomes larger and larger. So the reciprocal space crystal structure becomes smaller and smaller. And you now also very nicely see that the bands that are folded from higher brilliance zones in an extended zone scheme basically follow a free electron-like band structure where we have a gap at the point P, we have a gap somewhere in the middle between P and H because a band coming from other directions crosses here, etc. And these reasonably well follow free electron-like bands with an effective mass of 1. And we can go to potassium, and now we see that even more bands start to cross, we have more band folding. And then we go to rubidium, and that is even more increased, or cesium or francium. And some of those bands we will come back to later. We shouldn't explain them by free electron bands because they are also there because of atomic structure that we have. But at least we see that at the Fermi energy, the bands are always nicely given by free electron-like states. And the deeper we go in the periodic table, the smaller the brilliance zone, the more folding and the more bands that you see at higher energies. And actually we can also explain this from the atomic structure, that the higher the Z, the closer the principal quantum numbers are, so the lower in energy the additional atomic states are. Again, for those materials we will find that we can optimize simultaneously the atomic wave functions as well as the kinetic energy for free electron-like states. So I hope I've shown you now several examples where we see how free electron-like systems work, and that with this theory where we have a periodic crystal giving rise to a weak periodic potential plus the kinetic energy already is able to quite well describe the electronic structure in several of these materials. So what we will do in the next videos is discuss on how we can actually calculate effective potentials that enter into these kind of models. For that we will use Hartree-Fock and density functional theory. And for now, thank you for your attention. We see each other later. Stay healthy.